Good morning everyone, I am Mr. Ish. Thank you for joining me for this video. It's kind of dark, cloudy and rainy outside, so I hope the hue of this video is not too orange since I have all of these bulbs on, but I believe the presentation will be nice and clear. We're looking here at cross-sectional volumes, and I want to do everything here with regards to a cone because you can have a good effect come out with that. If you have a cone and you give it a three-dimensional appearance, what is a cross-sectional volume we're talking about? We know there's a certain zero here as a base and a certain height. If you were to slice out a good representation here with regards to a three-dimensional block and you pull this out, what are you looking at? You're looking at something which looks very much like this. And this right here is a cross-sectional slice. And this cross-sectional slice has dimensions in all three regards. A certain length, a certain width, a certain height, breadth, all of that. We're looking at the cross-sectional volume. How do you go about determining a cross-sectional volume of this block? And that's what we want to determine in this. We will be looking here at a cone and we can give it some hypothetical numbers here because I want to do something here concrete in terms of something which will require calculations, nothing conceptual. We'll be looking here at a cone, a right circular cone, which has a right triangle which can be generated from within it. It'll have a height. We'll give it a height of 10 centimeters. It'll have a radius. We'll give that a dimension of 3 centimeters. You know very well the volume of a cone has a formula 1/3 pi r squared h. As a good check, if you were to put all of these measurements in, you'll have 3 squared, which is a 9, times 10 divided by 3. You have a volume coming here for a cone with these dimensions to be 30 pi. Let that be the check to make sure that what we'll be doing will be correct. We will do a good equation of this with these dimensions given. We have to develop a good equation first, from which then we can use integral calculus to generate the cross-sectional volume of that slice, that three-dimensional block or slice, and then we'll proceed from there. I promise you it will be a very interesting video. A good way to start this is to start with an XY plane and we map it out exactly what we have, the height and the radius. The height will right here be 0, 10. The radius here can be 3, 0, and you have to find this line, the equation of this line, because that'll feed into that entire integral formula. If you were to rotate this area which is bound by this line and these x and y axis around the y axis, rotation at the y axis, you'll very well demonstrate and develop a three-dimensional cone. But we need to determine the formula of this line here. We have a 0, 10 and we have a 3, 0. The slope over here will be y2 minus y1 divided by x2 minus x1 will be minus 10/3. We have a y-intercept of 0, 10. Our equation here is minus 10/3x plus 10 right there. But since we have a vertical line of rotation, everything has to be presented in the x equals format. And our interval here must be from a vertical dimension 0 going all the way up to 10. Anyhow, this right here will become y minus 10 times minus 3/10, and that right there is the equation. This equation also very well represents the radius, because if you measure the distance from your line of rotation y-axis to any point on this curve, that right there is that dimension right there. And you know this will very well develop a circular cross-sectional slice having an area pi r square. Send that equation, which is also your radius, to this to determine your area with regards to y, because this area with regards to y must be integrated from 0 to 10 dy to give you your volume with respect to y. Anyhow, we have that in play, and let's clean this out a bit over here. It wouldn't be a bad idea to open this up to make it look better. You'll have a minus 3y/10 plus 3 slice pi r square. When you open that up, what are you going to get? You'll get a 9y square over 100 plus 9 minus, you're doing a minus b times a minus b. This is my a square plus b square minus 2ab, and this right here will give you 18y/10. But this 18y/10 can be simplified to minus 9y/5. This right here is my pi r square, the area with regards to y. This has to be integrated, and let's integrate it. We'll do our check procedure. Our check procedure is we make sure that this equation, everything is right, that when we do this integration from 0 to 10, we should get a volume of this cone to be 30 pi. Once it is, then we'll focus in on our exact cross-sectional volume determination, and we will talk about that when the time comes. When you integrate this from 0 to 10, you have a pi sitting outside. You have a polynomial which is very easy to integrate, and you're doing all of this dy. When you integrate it, definite integration, this will become a 9y cube over 300. 9y cube over 300. This here will become a 9y, polynomial integration, not hard. This here will become a minus 9y square over 10. You're doing upper limit 10, lower limit 0. 0 is meaningless. You're just bringing in a 10 only. And let's do it all over here. When you bring in a 10 over here, you get a 9 times 1000 is a 9000 divided by 300. We get a 9000 divided by 300. We can easily simplify that. I get a 30 over here. Here I'm getting a plus 90. Here I'm getting a 900 divided by 10, which is a minus 90. This cancels out. I get a volume here to be determined and calculated as 30 pi, which very well checks exactly what I have over here. So I know this equation right over here is good. It's perfect. Now all we have to do for a cross-sectional slice determination is to measure where we want to do our cross-sectional slice. And only some of this will erase, nothing else will erase, and I'll show you why that is the case. Because this here will still represent the equation from which we will determine the volume of the cross-sectional slice. All will change are the intervals that are involved, because the slice will be dependent on where we make the cuts. If we have a cone right over here and we know it looks something like this from 0 up to 10, and I want to cut it right over here and I want to cut it right here and then pull out this block, right, and let this part be here 4 and let this part be here 5. So I'm taking a cut which is in terms of height 1 unit, and I pluck it out and I look at it and it looks something like this, does it not? Right, it looks something like this. All I need to do is just put a 4 over here and I need to put a 5 over here. I have everything already in place to determine the volume of this cross-sectional disc, or you want to call it a cross-sectional slice, but it's more than a slice because it has a certain height dimension. But that block will be very well determined using this formula we already have in play. And you know the antiderivative is easy. Let's bring this pi and keep it out here. We have a 9y cube over a 300, right? We have a 9y. We have a 9y square over 10. We have to just bring in the 5 and the 4. Of course, you won't get a clean answer here because we'll probably end up getting a good fractional answer, but that's fine. We can do some simplification here. 9 and 300. 3 goes in 9 3 times. 3 goes in 100 100 times. Alright, now let's bring in the 5 and we'll bring in the 4 and then the difference of the 2, and we'll do all of that right here. We'll do 3 times 5 cube minus 4 cube, which is 125 minus 64 all over 100, plus 5 minus 4, remember upper limit, lower limit, 5 minus 4 is a 1 times 9 is just a 9, minus, we have a 9 over here, and then here we have a 25 minus 16, but all over 10. This right here has to be all solved, and let's do it. We have 125 minus 64 times 3 divided by 100. I'm getting 183 over 100 plus 9 minus 25 minus 16 times 9. I'm getting 81 over 10. Minus 81 over 10. We have a pi sitting outside. We can do a common denominator here of 100. We'll have 183 plus 900 minus 810, right? Because 10 goes in 110 times. We'll multiply with 81 and make it 810. We have here a 273 pi over 100 to be the volume of the cross-sectional disc, which would have arisen from that cut made at 4 and cut made at 5, and you're pulling it all out. And this answer would very well be right. You can convert this into a decimal answer, or you can leave it as is. Look right here, 30 pi representing the volume of this entire cone. 30 times pi, it gives you a value here of 94.25 units cube. You do 273 pi divided by 100, you get a volume over here to be 8. Let's round it up, 8.58 units cube. Look at the difference between this. This is the volume of the whole cone from 0 to 10. This right here is the volume of only that disc from 4 and 5. But you can see as you're making your cuts here at the base, the discs are larger, so the volume will be larger. As you make your cuts closer to the top where everything narrows out, then these volumes will be much smaller, and you have the equation already here. You can just, for your own fun, make these discs larger or smaller. You can do a disc here from 0 to 1 or 0 to 3 or 4 to 7 and see how the volumes compare, but that's on you if you want to do that. But this right here was a equation we needed, from which all you have to do was modify this to determine where the cuts will be made, and then from there you'll very well arrive at the cross-sectional volume of that disk you have generated from your solid. And with that, I thank you for watching this video. Stay tuned. Have a nice day.